Chemistry has been important since ancient times. The processing of natural ores to produce metals for ornaments and weapons, and the use of embalming fluids are just two applications of chemical phenomena that had been utilized prior to 1000 BC. The Greeks were the first to try to explain why chemical changes occur. By about 400 BC, they had proposed that all matter was composed of four fundamental substances: fire, earth, water, and air. The Greeks also considered the question of whether matter is continuous and thus infinitely divisible into smaller pieces or composed of small indivisible particles. Supporters of the latter position were Democritus of Abdera and Leucippus, who used the term atomos, which later became atoms, to describe these ultimate particles. However, because the Greeks had no experiments to test their ideas, no definite conclusion could be reached about the divisibility of matter. The next 2,000 years of chemical history were dominated by the pseudoscience called alchemy. Some alchemists were mystics and fakes who were obsessed with the idea of turning cheap metals into gold. However, many alchemists were serious scientists, and this period saw important advances. The alchemists discovered several elements and learned to prepare the mineral acids. The foundation of modern chemistry was laid in the 16th century with the development of systematic metallurgy, extraction of metals from ores, by a German George Bauer, and the medical application of minerals by a Swiss alchemist-physician known as Paracelsus. The first chemist to perform truly quantitative experiments was Robert Boyle, who carefully measured the relationship between the pressure and volume of air. When Boyle published his book, The Skeptical Symist, in 1661, the quantitative sciences of physics and chemistry were born. In addition to his results on the quantitative behavior of gases, Boyle's other major contribution to chemistry consisted of his ideas about the chemical elements. Boyle had no preconceived notion about the number of elements. In his view, a substance was an element unless it could be broken down into two or more simpler substances. As Boyle's experimental definition of an element became generally accepted, a list of known elements began to grow, and the Greek system of four elements finally died. Although Boyle was an excellent scientist, he was not always right. For example, he clung to the alchemist's views that the metals that were not true elements and a way could eventually be found to change one metal into another. The phenomenon of combustion evoked intense interest in the 17th and 18th centuries. The German chemist George Stahl suggested that a substance he called phlogiston flowed out of the burning material. Stahl postulated that a substance burning in a closed container eventually stopped burning because the air in the container had been saturated with phlogiston. Oxygen gas, discovered by Joseph Priestley, an English clergyman and scientist, was found to support vigorous combustion and was thus supposed to be low in phlogiston. In fact, oxygen was originally called dephlogisticated air. By the late 18th century, combustion had been studied extensively. The gases carbon dioxide, nitrogen, hydrogen, and oxygen had been discovered, and the list of elements continued to grow. However, it was Antoine Lavoisier, a French chemist, who finally explained the true nature of combustion, thus clearing the way for the tremendous progress that has been made near the end of the 18th century. Lavoisier, like Boyle, regarded measurement as the essential operation of chemistry. His experiments, in which he carefully